Hi, welcome to this lesson on Euclidean geometry, the proportionality theorem. So let's have a look at what the proportionality theorem is. So as in all theorems, there's a statement that goes towards it, an if and then statement. The if part, the hypothesis, includes all the information that we assume, so the given information. And then the conclusion part, the then part, is the thing that we're trying to prove. Okay, so this is what we call the forward direction of the proportionality theorem. The proportionality theorem is what we call an if and only if statement. So the backwards or converse of this statement is also true. And we'll have a look at that. Okay, so what does the statement say? It says that if a line DE is drawn parallel to one side of triangle ABC. So here's triangle ABC here. So let's say we extend it either outwards or even inwards. We could have DE over here, for example, as well. So we just want another side that's parallel to that base that we've chosen. So that's the given information. So the only given information is that you start off with a triangle ABC and you just have another line DE that's parallel to it. Then the conclusion part says that this will divide the other two sides, so the non-parallel sides, into the same proportion. So that means that AB divided by BD is in the same proportion as AC over CE. And you can see I've written it like that. So KX over KY, the K's will divide and you're left with X over Y. And on this side you have MX over MY, and the M's will divide and you'll have X over Y. So that's why we say the two sides are in proportion. That's why we call it the proportionality theorem. So it deals with triangles and parallel lines. So that's the basis of this theorem. And then the converse statement is also true, so that if you have a line that divides two sides of a triangle in the same proportion. So if we know the line DE, right, we've just constructed it and we've got this proportion happening. This proportion is true. Then we can conclude that the line that we drew there is parallel to the third remaining side. Okay, so it's an if and only if statement. So let's have a look at the proof of the forward direction. So there's a bit of construction. So we know that when it comes to Euclidean geometry, the proofs usually follow the same structure. You start off with the given information, the hypothesis, and then you create a smart construction within the triangles to enable you to prove the conclusion. So what is the construction we're going to consider? So first of all, the hypothesis just says you have triangle ABC and you have another line DE that's parallel to BC. Okay, that's all we're given. So now we are going to construct some line segments. So what is the key here? So we're going to draw H1 from this endpoint E so that it's perpendicular to this base AD. And then we'll do the same thing from the other vertex D. We'll draw a perpendicular line that's perpendicular to the base AE. All right. And then the other two constructions we'll do is we'll construct B to E and C to D. So these are the two main constructions. Once we've got these constructions, we're then going to use the results we know about proportionality of triangles and parallel lines. So first of all, look at the area of triangle ADE, this large triangle. It's going to be half times the base AD times that perpendicular height we constructed. So that's why we constructed it. And then if we take that ratio of the area of triangle BDE, so this smaller triangle over here, then that area is going to be half times the base BD, but that base BD will also have this perpendicular height H1. Okay, it's just outside the triangle this time. So that gives you half BD times H1. So why did we do this? Well, what we've shown now is that the area of that large triangle ADE to the area of the smaller triangle BDE on the same base, this big base here, that we can simplify it. Okay, halves divide, H1s divide, and we're left with AD over BD. So essentially what we've shown here in this first part here is that if you consider the areas of a big triangle ADE over here, so this is ADE, and we look at the smaller triangle BDE, so BDE, you can see that DE is a common side length that's shared. But what we've shown is that the area of this guy, if we call it A1, and the area of this guy A2, we've shown that the ratio of those areas is essentially just this larger base AD divided by the smaller base BD. That's what we've shown. Okay. Now we'll do exactly the same kind of idea, but on the opposite side now. So now let's look at triangle ADE again. Okay, the big triangle, but this time we'll take AE as the base. And then we'll look at the smaller triangle CDE as well. So essentially we are mirroring the proof of the first part we just did. So again, the area of triangle ADE is going to be the base AE, a half of that base, times this perpendicular height H2. And the same thing here for triangle CED. It's going to be the base CE times this perpendicular height H2 times a half. So these will divide out again, and you're left with AE over CE. So again, what we've shown is that this bigger area, triangle ADE, and then the smaller triangle, CDE, okay, again, a common shared side. We've shown that if this is area A1 and this is area A2, what we've shown is that the area of the bigger triangle divided by the area of the smaller triangle can be just simplified down to the base of the bigger triangle divided by the base of the smaller triangle. Okay, so if we come back now, can you see that the area of triangle BDE, okay, so let's just clear this up so we can see it more clearly. So now I'm going to compare areas of these two smaller triangles down here. So notice that triangle BDE, this one here, and then triangle CDE, this one here, they share a common base DE, and they are between two parallel lines, BC and DE, that subtend to that parallel line. So we know that two triangles with a shared base that subtend to the opposite side of a parallel line must be equal in area. So this is where we get area of triangle BDE equals area of triangle CED. So let's just keep breaking down what we've been doing step by step. We found a ratio of the areas of the bigger triangle to these smaller triangles. And now we've looked at these two smaller triangles in particular and noted that their areas are equal by this exact reasoning. Okay, and then lastly, what we're going to do is now take the area of these two larger triangles, ADE, and divide it by these smaller areas of triangle BDE. That's what we did, right? And so area of triangle ADE over the area of triangle BDE we said was just the base, this big base AD, over this small base BD. So that's where we get that. And then we said that the area of this big triangle with the small triangle is just the ratio of the base of the big triangle divided by the base of the smaller triangle. But why do I have equality here? Well, let's have a look here. These two areas in the numerator are equal. It's the same triangle, ADE. But we've shown in this previous step that those two small triangles are equal in length. So these two triangles are equal. So therefore, this entire equality here is equal, this proportion here. So what have we actually shown? We've shown that AD, so this long side divided by the short side, is in the same proportion as this long side divided by that short side. So that is the proportionality theorem, but it's not exactly the way we stated it. So lastly, I'm just going to simplify it a bit. So let's see what we have here. In this triangle, so the bigger side, AD, over the smaller side, BD, I can deconstruct that. AB, the long side, is AB plus BD. It's this side plus that side. So because BD is just a single denominator, I can separate it out. AB over BD plus BD over BD. But BD over BD is just 1. So that's what I end up with. Okay, and then similarly here, we showed that this big side AC over CE, right, that is equal to AD over BD, but I can break it up. So AE is just AC plus CE. Okay, so this big side AE is the sum of these two smaller sides. And again, if I divide that out, AC over CE plus CE over CE, but CE over CE is just 1. Okay, we've just proven that these two guys are equal. Okay, that's what we've actually proven in the proportionality theorem. Okay, so therefore these two things must be equal. But one is common to both, so I can subtract it. So this is the final conclusion part of the theorem that we were showing, is that this side here, AB divided by BD, is the same as AC over CE. And that is the proportionality theorem. Okay, it works in both ways. You could take the larger side to a smaller side. It'll be in the proportion of the other larger side to smaller side. Or you could just take the two smaller sides and look at them in proportion. Okay, so both ways work for the proportionality theorem. Right, and to end off this on the proportionality theorem, there's a nice result that follows directly from the proportionality theorem, and it's the so-called midpoint theorem. So to state the midpoint theorem, it's an if and only if statement, and it says that if triangle ABC has midpoints, so that's why we call it midpoint theorem, on the side A, B, and D. So now, just like the proportionality theorem, what happens is now that we choose the points so that they are midpoints of the other two sides. That's what's special about it. It's a special case of the proportionality theorem. Then the conclusion says that the line that DE joins from those two midpoints is parallel, okay, to that third side. And moreover, the side length of the bigger side, BC, will be twice the distance of the other parallel line. Okay, and the converse of the midpoint theorem is also true, that if you know a point goes from a midpoint to another point here, and they are parallel, then that other point is a midpoint of the other side. Okay, so the midpoint theorem is just a special case of the proportionality theorem where we can actually work out the sides of the third, the distance of the third sides. All right, so that is the proportionality theorem. Now that we've developed that theorem and we've proved it rigorously, we can go ahead and apply it to some questions. I'll see you in the next one.